General relativity, step by step. I've been talking about transformations between one coordinate system and another. And I've got this kind of rather peculiar coordinate system here. I'm going to draw this again, but I'm going to emphasize something slightly differently. Now, which way around did I do it? I had the I've got the y lines red and the x lines blue. Okay. So here's my Cartesian coordinate system, nice and regular, and that's x equals -1, 0, 1, 2, 3. And on my other system I had here, that's h equals -2, h equals -1, 0, 1, and 2. That's y equals -1, 0, 1, 2. And here I had theta. This was a little bit difficult to draw. That's not bad. Theta equals 0. Theta equals no, that's theta equals pi by 6, pi by 4, and so on. What I want to do now is to move around on this surface here. Being a little bit coy about exactly what I mean. But I want to move around. I might be sort of here, and I might want to go there somewhere else. I'm only talking about moving small distances. If I start moving a huge distance, you can see that moving from here to here, well, even from here to here, then the angle of the angle of the red lines changes, and so that causes problems. I want to move small distances, small enough for me to be able to neglect anything above the first order. So let's have a think about how I can do that. Of course, what I want to do is to set up a little sort of two vectors, vx, let's say, and vy, in a nice way here. So I can decompose this vector here into its components nicely, and then I can use that to describe a velocity field on this surface. If I've got little water molecules running around over it or something like that, then that's the kind of thing I can do. Yeah, I'm going to call that EX, and I'm going to put a little thing under EY to show that it's a little. I'm going to be a little bit coy about it. I'm not defining it super rigorously, but enough. Enough rigor for general relativity, I think. I hope. Okay. EX and EY. What do I mean by that? EX equals what? I need to come up with a definition or a way of thinking about it that means that it will translate into this system here, bearing in mind that my coordinates could look really complicated. Remember the very complicated. Here we go. The coordinates might look like that. I mean, if you've got space-time near a couple of orbiting black holes, then goodness knows what might happen. So we need some way of thinking about this. And the way I think about it is I think that EX with a little line under it equals what happens when the x coordinate changes from x to x plus delta x, and of course, and you keep everything else constant, and so you might be here and then you change x a little bit and you move along here, and so that's what I mean by this EX here. So you see it written in different ways, and I'm not happy with any of the notations that I've seen in the books, frankly. I don't think they're very good. And I don't have any massive improvement over it. But I do have one thing which I've not seen anywhere else. That's a way of writing it. Di P by di X, where P equals the point defined by coordinates X and Y. So EX is what happens, or where the point goes, when you change the coordinate x a little bit. And of course EY is the same thing here. EY equals di P by di Y, where P equals P of x comma Y. And that seems to work. I mean, what you'd like to do is to take this coordinate basis here and stick it onto this coordinate system here, but that doesn't help, because there's a complicated and unhelpful relationship between the direction of these little arrows and the way that your coordinate lines work. So I'm going to define EH equals, by definition, di P by di H, which is what happens when this horizontal axis changes a little bit, this horizontal direction changes, equals di P of H theta by di H. And of course E theta equals di P by di theta equals di P of H theta by di theta. So what happens, and that's a little vector here. So what happens when theta changes? Now it's a little bit hard here because we've got a rather, well, deliberately so, we've got a rather confusing relationship between the two. We've got x equals h, y equals h tan theta, and of course we've got h equals x and theta equals arc tan y over x. So what does that mean? What does it mean to change theta? What does this curly die mean? What that curly die means at fixed h. And of course what that means is that we've got to fix h at a particular point, and we've got to consider theta at a particular value. So these guys here, this EH and E theta, these move about. These are not constant. In the Cartesian case, I hesitate to say boring, convenient I suppose is the right word, EX and EY don't change. They're in Cartesian coordinates, these guys are constants, but these guys move about. So let's try and figure out what this di P di H, let's think about what that means. That's di P by di H. Let me just draw, I'm going to draw it again. Let me pinch in a little bit, and I'll draw these again. So just remind myself what colours I've got. I've got blue vertical lines. Let's draw those. Come on. My tablet is playing up. Just a second. Oh, I didn't mean to do that. So I've got blue lines of constant h, and I've got red lines of constant theta, which look like, oh dear, not looking very good, but there you go. Actually, I'm going to draw that again. Maybe if I start there, that's better. Draw it this way. There we go. So they're lines of constant h. So that's theta equals theta 1, theta equals theta 2, theta equals theta 3. So I've got my little point here. Let's have a look at the first one. What happens when we change h? Well, I'll go back to blue. That's h equals h1, h equals h2, h equals h3, h equals h4, and so on. So what happens when we change h? Now the thing is that we're changing h, if I go back to black I can write on here, at constant theta. So because it's constant theta, when I change h, I might go from that line to this line here, but you can see I've got to maintain theta constant, so it climbs up this red line here because that's a line of constant theta. So that little axis there, that's what I mean by this basis vector here, di P di H. And of course what di by di theta means is that we've moved theta up a little bit, but we're not allowed to change h. So we've got these two, oops, I'll just draw that again. We've got two little vectors, and I'm being a little bit unhelpful about the exact direction. So which one's this one? This one here is what happens when you change h. So that's EH. I'm not drawing it particular, and that one there is E theta. Okay, so now we need to figure out what these things are. Now, oops, I'm not sure what happened there. There it is. So let's have a look at that. EH equals di P di H at fixed theta. You don't normally write at fixed theta. You don't normally need to write that. That's kind of understood. Now what I'm going to use is the thing I introduced on the very first screencast about total derivatives. So I'm going to say it's di P by di X, di x die h plus die p die y die h, and this is equal to eh equals. Now things start to get a little bit clever. I'm going to observe that that thing there, die p die x, is just this one here. That's just ex. I like this way of working. What I'm doing is I'm almost treating e sub x and e sub y as primitive little vectors that I understand. They're kind of primitive isn't the right word. They're kind of a more fundamental concept. What I'm trying to do is, I've got this thing EH and E theta as well, which I'll come to in a minute. I've got these things which I don't understand. I don't know what they are, and I'm using trig and all sorts of stuff. It gets a lot worse in 4 dimensions. I don't understand what they are. So what I want to do is to link them to these EXs and EYs, which I do understand, because I'm very happy, we all are, with Cartesian coordinate systems. So, oh look, and of course that's EY. Now what's dx dh? Let me just remind myself what the relationship x equals h and y equals h tan theta. So I can expand this little thing here. Let's just get rid of all this. I can expand this. EH equals di p di x, which is just EX, because that's what happens when you move the x Cartesian coordinate and leave y alone, times dx dh, which is just 1. Plus di p di y is just EY vector di y di h. That's this formula here, tan theta. Oops. Tan theta. There you go. And of course we can do the same with E theta, which equals di p by di theta, which equals di p di x di theta plus di p di y di theta. Riding slipshod over a whole bunch of notation here. Oops. And I'm going to use these formulas here. Equals EX times dx di theta. Dx di theta is just 0. Plus dp dy. Di p di y is just EY. Di y di theta is this one here, so it's H. Oops. H times the differential of tan theta with respect to theta is sec squared theta. So now we've got EH equals EX plus EY. As I say, I've seen loads of different notations for this. When I call EX, I'm writing it like that. The notations I've seen are DX with a twiddles over it, or is it an arrow? I can't remember. I've seen di by di x. I've seen loads and loads and loads of different notations, but I'm just going to stick with EX. EH equals EX plus EY tan theta from here. And E subscript theta equals EX times 0 and EY times H sec squared theta. So there they are. At any particular point, let me go back. Oh, I'll draw it again. My system's not being very responsive today. Here's my lines of constant h. Lines of constant theta look like this. I'm at a little point here. So I want to work out what EH is. I better do it black. There it is. I want to work out what EH. It's EX plus EY tan theta. So it goes along there a little bit, and then it goes up there, and that vector there, this one here, is E subscript H, which we kind of knew anyway, because when we change H, when we go from this line to this line here, or gone about halfway there, but we're not allowed to change theta, so we go up there. And what does E theta look like? E theta looks like EY times H sec theta, so that cruises up here, and of course something very serious is going to go wrong at theta equals pi by 2. So, and this one here is E subscript theta. These things here are called coordinate bases. And they allow us, if we're going to start fooling around with vectors, what the coordinate basis allows us to do is to have a coherent and consistent view of how vectors behave in a curvilinear coordinate system. And we'll see other advantages too. So I'm just going to leave it like that. I'm going to state it again. So EH equals, let's pinch in a little bit here. EH equals di P di H equals di P of H theta by di H. And we know that equals di P di X di H plus di P di Y di H. So we need this one and this one here. Looks like a dot, doesn't it? Better get rid of that. X equals H, Y equals H tan theta. We're just blowing it in. EX dx dH is just 1 plus EY di Y di H is just tan theta. Notice carefully that EH gets longer and shorter. Depending on where you are in your plane, depending on where you are in your world. Of course, if I change theta by a little bit here, you see we're going miles and miles and miles up here. So EH gets longer and shorter in different parts of the plane. Well, that's just tough. That's just the way it is. We'll see examples later on where this becomes very important, especially when it becomes a singular point. We'll see places where it's really important. A lot of people spend a lot of time, if you look at elementary vector calculus stuff, you will quite often not just see this, but you'll see the equivalent of this equals a unit vector. Do not pay any attention to that. That's enough to drive you crazy. You've also got E theta hat, which is a unit vector. No, it's just crazy. It's just nuts. These vectors change their length in a perfectly sensible way, in a perfectly sensible and coherent way, as you move around this non-Cartesian coordinate system. And so what people do is say, oh, we don't like the vectors changing length. We'll keep them the same length. But what you've got is a vector system which is like that, and then it sort of rotates around depending on where you are. Well, if you're going to rotate it around, you may as well change the length as well. So no, don't bother about that. Right. Oh, this has been a long one. Yes, it's longer than I intended. I'm going to stop here.